we now have a way to compare our measurements against a hypothesis that, well, mostly only makes a claim about the expected value of a set of measurements. It doesn't say anything about the rest of the distribution. Now, is there a way in which we can take the entire distribution that we have in mind into account? Of course, the answer to that is yes. These are called goodness of fit tests. And in this video, I'm going to talk about two of them, the chi-square test and the Kolmogorov-Smirnov test. The most famous, perhaps, is the chi-square test. And the idea behind this test is that we start from some hypothesized distribution and we partition it into a number of bins. We say k bins. We are going to perform our experiment n times and count how many of the experiments end up in which bin. Formally, counting the number of experiments in each bin gives us a number of stochastic variables. Let's say y, subscript b and n, b for the bin number and n for the total amount of measurements that we're going to do. And ybn is the number of stochastic variables that fall into this bin, the number of experiments that fall into this bin. Of course, we can compute the expected value of this count from our hypothesized distribution. For our test, we then compute the so-called chi-square statistic, which is, well, it looks basically like the variance in the number of actually counted experiments in a bin minus the expected number of experiments that would fall in that bin, that to the squared divided by n and divided by the probability of indeed finding an outcome in a bin. That chi-square statistic can be shown to converge towards what is known as a chi-squared distribution with k minus 1 degrees of freedom, where k was the total number of bins. The chi-square characteristic always has a positive value, and when we get a better fit, we expect it to be closer to 0. So in order to compute a confidence interval, we take our confidence level p and we look at the right tail of p in the distribution. For example, concretely, in our example, we compute a chi-square value of 2.564 on the basis of our measurements using 12 bins, and the 99.9% confidence level at 12 minus 1 degrees of freedom is 31.3, which is clearly much bigger, so we cannot reject our hypothetical model on the basis of these measurements. We will accept that it might be a good model. As a final remark, the chi-square test, just like the central limit theorem, depends on convergence in the limit to the chi-square distribution. And in practice, generally speaking, this convergence is faster if the bins are equiprobable, if they have roughly the same expected value. And it helps also if this expected value is larger than a value of, say, 5, because you actually want experiments to end up in these bins. So n needs to be large enough to make sure that there are at least 5 experiments ending up in each bin based on the expected value. And pay attention that the bins are a partitioning of the distribution, which means that they do not overlap, but they actually touch. And the outer bins are going from minus infinity to infinity on the right and on the left and on the right. One way to think about the chi-square test is that it determines a confidence level based on the distance between the probability density function or the probability mass function that you hypothesized and the histogram of the measurements that you found. The second type of test, the Kolmogorov-Smirnov test that I would like to discuss, does not determine the distance between the probability density function and the histogram, but between the cumulative distribution function and the cumulative distribution that is associated with the measurements. Let f hat be the cumulative distribution function of our hypothesized distribution. We can then define f tilde as the approximation of this function at any x by simply counting the relative number of outcomes that are below a certain value. And the Kolmogorov-Smirnov test is then based on computing the maximum difference between these two functions. That gives us a stochastic variable d of n, where n is simply the number of experiments that we did. To describe the way in which this stochastic variable d of n is distributed is rather complicated. In fact, for discrete distributions f hat, the distribution d of n is dependent on the exact distribution f hat. But for continuous distributions, there has been an approximation that at least allows us to compute the relevant quantiles and critical values that we need in order to do a test. So we can compute the tail of the distribution of d of n by this lookup table. And the way that lookup table works is that you have this value c determined by the confidence level. So for a confidence level of 95%, the value of c is 1.358. And the n value is the number of experiments that you've performed, which in our case was 133. So when we've computed the stochastic d of n, we should find a value lower than 0.116 in order to accept that the distribution is indeed close to the actual distribution that we hypothesized. If d of n is larger than 0.116, then we reject our hypothesis. As you can see, the Kolmogorov-Smirnov test does not rely on any kind of limit. That means that it is also accurate if n is small. That does not mean necessarily that it is also more useful if n is small. It still depends on the kind of distribution, which experiment, which goodness of fit test will be best at rejecting hypothesis. But it does mean that it is more meaningful if you have small values that you use the Kolmogorov-Smirnov test. Unfortunately, the Kolmogorov-Smirnov test is only available so far for continuous variables. There are computations for discrete variables as well, but these are very much more complicated, and I'm not going to discuss them in this video. If we perform a chi-square test, so we're basically taking this difference between a histogram and a distribution function, whenever we have that probability density function or probability mass function, the visualization is quite easy. If you're performing a Kolmogorov-Smirnov test, the visualization is not so natural, because all these cumulative distribution functions in one way or another look like S-shapes, and S-shapes to the eye are not that easy to interpret when they have small changes to them. Now there is a trick to this, and that is to use either a PP or a QQ diagram. So instead of trying to compare two cumulative distribution functions, we might just take one value on the quantile axis, the horizontal axis, and look at which two values this gives us on the vertical axis, on the probability axis. And these two values can be used as an x and a y coordinate in a probability plot. If we plot these two values while we range over this quantile axis, we get something that should be a straight line if there were a perfect match, but often deviates from this straight line a little bit. And visually, checking whether something deviates from a straight line is easy. Now, similarly, we can also vary along the probability axis and look at where the values end up on the quantile axis, and then we get a QQ, a quantile-quantile plot. Often it is easy to recognize differences that are around the median or mean in a probability plot, and it is easier to recognize differences in the tails of a distribution in the quantile-quantile plot. Whenever you perform goodness of fit tests, consider, even if it's just a chi-square test or a Kolmogorov-Smirnov test, to include pictures of this probability plot, the quantile-quantile plot, and a probability density function together with a histogram into your reporting, because also this gives the reader a good idea of the kind of things that you're doing, and it's more useful than just these numbers for the chi-square value or the ks value. You now know how to set up a statistical model and phrase a hypothesis in terms of a mean and a variance, or an entire distribution. And you know how to carry out experiments to test whether the outcome of the experiments is in line with the hypothesis or not. Basically, you can test whether it is not in line. A warning is still in place, because this is still statistics that we're doing, and you run the chance that you have not done enough experiments to make your hypothesis test converge. The central limit theorem and the chi-squared test, they both depend on having enough experiments to make sure that the statistical variable that you compute actually converges to this desired distribution. There's also the chance that your experiments are not identically distributed, that something has changed throughout you performing these experiments that made the distribution change overall, or that they are not independent. You have to check for this somehow. And finally, there is still the chance that you accept a model even though it is wrong. That's called a type 1 error. A type 1 error cannot be prevented. That's the scientific method, right? You cannot check whether something, you cannot guarantee based on experiments that your model is right. So there is always a chance of accepting a wrong model. And on the other hand, because it is statistics, there is also always a chance of rejecting a model that is actually correct. That is called a type 2 error. But for the type 2 error, we know how to bound it, because we can compute usually a confidence level. And that confidence level tells us how big the probability is that we've made a type 2 error. For a type 1 error, the power of a test, we cannot compute such a probability, at least not without making more assumptions. And if you want to know about that, I suggest that you dig into statistical theory a little bit deeper on yourself. Still, the methods that you've learned so far are a basic Swiss Army knife for engineers to understand how statistical models work, and they are already very useful if you have to interpret measurements in practice, or if somebody else has done some measurements and you want to ask a few critical questions.